It is 2 o'clock, and I would like to welcome everybody to this doctoral thesis defense. Of course, I'd especially like to welcome the doctoral candidate, Yukihiro Kusano, and the two official opponents, Professor Dennis Dowling, Director of the IFORM Advanced Manufacturing Research Center and Surface Engineering Group at the University College Dublin, and Professor Alexander Friedman of the John A. Nyhan Chair and Director of the Drexel Plasma Institute, Drexel University. We're very happy that you would come here today and join us for this defense. I also welcome Professor Jens Juel Rasmussen, Department of Physics at DTU, and he's the chairman of this assessment committee. My name is Katrine Krogh Andersen. I'm Senior Vice President at the Technical University of Denmark and the Dean of Research. And I will be the chairman of today's procedure. The proceedings are as follows. After my small introduction, the doctoral candidate Yukihiro Kusano will present his thesis, Atmospheric Pressure Plasma for Polymer Surface Modification, Alternating Current Gliding Arcs, and Ultrasound Enhanced Plasmas. It's a lecture of about 30 minutes. After this lecture, I'll ask whether there are exauditorial opponents. In case anybody wishes to take the word, they should announce it at this stage after the presentation. I will thereafter give the word to the two opponents who will discuss the thesis with the candidates. And then comes the possibility, in case we have exauditorial opponents, also they will take the word after the two official opponents. After these discussions, the formal part of the defense is over, and the opponents will meet to finalize the evaluation, while the rest of us can go outside this room and participate in a reception by DTU for the doctoral thesis. And you will then join us after your final evaluation. The degree of Dr. Technicus is officially awarded by the Academic Council of the University, and that means that they would take up at their first coming meeting after today, which I think is in the beginning of May, and that's where it's officially decided whether you will be awarded the doctoral degree. Before I start, I'd just like to acknowledge that wind energy technology and research and development around it has been a major stronghold for Denmark for decades. It's therefore also of high importance for the university and for Denmark that our research in this area continues to be at the forefront, and that we have front runners like Yuki who use their special knowledge, their forefront research, to use it in a cross-disciplinary way to advance our work within the wind energy. Also goes for many other areas, but this is really one of our strongholds and where we have to keep up and have to remain in forefront. And I think this is nicely manifested by the work that we're going to hear about today. With this, I'd like to invite you, Yuki, to go to the podium and present your work on atmospheric pressure plasmas. Welcome. And I'll take my book with me.
Thank you very much for a nice introduction, and thank you everyone for coming to my presentation. My presentation today is about atmospheric pressure plasmas for the surface modification of polymers. I'd like to start my presentation by introducing briefly about the relation between wind energy and the plasma. Then I'm going to give a few words about adhesion and plasmas in general. Then I'm jumping into the objectives of my thesis. Then there are two big topics in my thesis. One is gliding arc. And probably I have to spend the majority of the time for the introduction and also gliding arc. But another important research is ultrasound enhanced plasma. A plasma with the introduction of acoustic energy. What can happen? That's what I've been doing. Then, if time allows, I'd like to give some words about future perspectives. Okay. Wind energy and the plasma. I've been trying to have some interesting interactions among a variety of colleagues But among all, as the person who is working on materials research for many years, it's very natural to work on something for manufacturing of wind turbine blades. That is what I'm studying now. Specifically, it is about the production of lightweight composites. That's the main part of the blade. And then once we work on it, there are a lot of interfaces of dissimilar materials. So we have to think about how they can interact. This is the cross-section of the blade. In general, it's a hollow structure, and the main part is glass fiber or fiber reinforced polymer. There's obviously the interface between fibers and polymer, and also these are combined together with glue. So combining adhesion is also necessary. And plasma technology, plasma processing has been already widely used for improving adhesion of materials. Therefore, it's a kind of obvious potential contribution I can do for the wind energy industry. Okay, then I also want to have some words about adhesion. You may think it's easy, but it's very, very complicated phenomena. There are three important effects which can control good adhesion. One is mechanical adhesion, mechanical bonding, chemical bonding, and also dispersive interaction. You know that if you roughen the surface, you can increase the surface area so that you can increase mechanical interlocking. That's well known. And also it's nice to have some chemical interaction like covalent bond or ionic bond. But in reality, in many cases, or in most cases, especially for wind industry, hydrogen bond usually plays the dominant effect for good adhesion, because it's not easy to have covalent bond or ionic bond. The range of the force is a bit diverse, and hydrogen bond is a bit weak, but nevertheless, it's very, very important. However, we cannot forget about dispersive force. It is very weak van der Waals force. But in reality, for the adhesion, you introduce a resin or adhesive to the surface, then there's the problem of wetting at the beginning. If wetting is not good, then you will create a lot of tiny defects or voids that they will be quite problematic for the adhesion. And then if it is wetting, both hydrogen bond and dispersive forces controlling parameters. Then after curing, gluing, stronger interactions with mechanical and chemical stuffs play important role. That's the adhesion. And then in the later part of my presentation, I often mention, for example, oxygen content or oxygen-carbon ratio on the surfaces. This is related to wetting of materials. If oxygen content is higher, typically you have more polar surfaces, so that it can have a similarity to the adhesives. Therefore, wetting will be better. So that's about it. Then here comes with plasma. In my area, plasma is an ionized or partially ionized reactive gas. So shortly speaking, it's a reactive gas. Then obviously it can be used for chemical processing. How it can be generated? By introducing electrical energy. Then you can get plasma. But more specifically, in my area of polymer material processing, we usually prefer so-called low temperature plasma or cold plasma or non-equilibrium plasma. In this type of plasma, electron temperature is not low at all. It's very, very high. It can be around 10,000 Kelvin or more. It can be around, it corresponds to around 1 eV or more. So that this kind of hot stuff can interact with the bonding, because the range of the energy is comparable. On the other hand, because of the low temperatures of heavy particles like atoms and molecules, they will not severely damage, and they will retain the chemical property of the gases. So therefore, we can change the surfaces, but because of the low temperature of heavy stuffs, we don't have to severely affect bulk properties. But I have to mention it later on, because there's something relevant to this topic. And this type of plasma can be very easily generated at low pressure. But in some conditions, you can get it also at atmospheric pressure. And this is what I've been doing. And for the application of the adhesion improvement, we can expect many quite important effects at the same time. That's why people are using it. First of all, plasma can clean the surfaces, remove weak domains of the surfaces, so that you can roughen the surfaces, so you can expect mechanical effects by plasma. But in my presentation, I have to omit this part because of the limited time. But then, on top of that, you can expect chemical modification, more specifically wetting the surfaces for better wetting and better interaction with glue. We can expect these things at the same time using a plasma. Okay, then it is clear that I'm not only working on plasmas, because I need a material to be treated. Then I need a kind of testing for the treated ones. But first of all, in my research, I have to diagnose, characterize the plasma by various techniques and have some theoretical approach. But characterization of the treated, modified surface is also important. Having the wetting test and also elemental compositional analysis and detection of radicals in the materials, which I have used in this presentation. But also for the adhesion research, it is a kind of a must. We have to verify the treatment effect is useful for eventual improvement of mechanical properties. In this sense, doing mechanical tests, having the treated surfaces bonded together and breaking it, that is something we are heavily working on. So that's the scope of the work in this thesis. So I hope you are not very confused. Then, coming back to the plasma, you cannot just get low temperature plasma just by introducing energy to a gas. You can accelerate the electrons, then electrons can immediately collide with molecules or atoms because of the very short mean free path. Then, if it is inelastic, gas is heated, and then electrons will be decelerated. In order to keep the plasma, you have to introduce the power. Then plasma is heated and heated and heated immediately, and you will have the thermal equilibrium plasma in a short time. But of course, this can be used for thermal processing. But for the materials processing, in many cases, it is not very desirable. So we have to avoid to become an arc discharge. Keep the plasma in the non-equilibrium condition is important. Then, since it is quite relevant, I'm going to introduce two very different plasma sources which can be operated as the low temperature plasma. One is dielectric barrier discharge, called DBD. Applying alternating current power to two electrodes but having the insulating plate in between so that you can block DC current, so that heating, too excess heating of the plasma can be avoided. It's really, really robust technique, and probably it is the most widely used atmospheric pressure plasma source. And it is very stable. But one problem is that you can generate this kind of plasma in a tiny gap, only several millimeters. And although I said it is low temperature plasma, if you want to increase the speed of the process and you increase the power, then plasma can get into a thermal plasma, or arc plasma can be generated. Therefore, there is a power limitation. And also, as you can see, in some conditions, plasma can be shower-like, filamentary micro-discharge is generated, and then subsequent surfaces can be treated non-uniformly. So uniformity can be also a problem. Then next one is gliding arc. Gliding arc has a very long history. That it was used since 19th century, if I understand correctly, and there are a lot of nice applications from that. But you typically need two diverging electrodes applying voltage between them, having gas flow, then there's the ignition, then it becomes immediately arc. So you are already in the arc stage, but plasma is extended by gas flow and heating by the voltage, but cooled by the gas flow. Then at some point, because of the increase of the surface area, cooling overcomes heating. Then it becomes to the non-thermal, non-equilibrium condition. That's quite nice. That can be used for the normal polymer processing. Then extended gliding. Then at some point, re-ignition, and then plasma, non-equilibrium plasma can be extinguished. That is a life of the gliding arc. In this sense, gliding arc is not an arc, but quenched plasma coming from the arc, but cooled down to the non-equilibrium condition. It is potentially quite interesting because initially it is an arc, then impedance of the plasma is quite low. Therefore, it's very easy to introduce very high power without any serious problems compared to normal low temperature plasmas. But in reality, especially in my previous experiences for the commercial gliding arcs, the lifetime of the non-equilibrium plasma is relatively short. Extension of the plasma is quite short, and also typically it has a low treatment effect. But because of this kind of very interesting potential, I wanted to tackle with the solution for having nicer performance of the gliding arc. That's a kind of motivation, and so I'm already talking about something about that. So the essential motivation was to have the higher speed, efficient treatment of the plasma devices. Now, of course, it is quite important to understand what is happening if I do something different from normal. Then first part of the talk, main talk, is about gliding arc. And then I'd like to talk also about the plasma with acoustic energy. This is another way of having the improvement of the treatment, because you don't have to introduce electrical energy for heating the plasma, but having additional effect by acoustic energy. That's the idea for adding ultrasound. But then later I combined these two to see if it works. That's the scope. But I think I will mainly talk about the first gliding arc. Yes, so I have used some commercial gliding arcs for many years, even when I was in Japan. But everyone thought it's not very efficient. But I speculated what is happening. Then my feeling is that power introduced to the plasma is quite low. And also the gas flow to extend the plasma is too high. And in my feeling, they want to have a longer life of the device, Therefore, they want to not to damage the device. That was my impression. And then for the fast processing, it's necessary to have higher power. And then I should try with the moderate gas flow, not to heat too much of the plasma. These are the starting points for trying. Then obviously the electrodes were heated too much. Then it's an obvious solution to try to cool the electrodes. That's why I was cooling the electrodes. But interesting, it's interesting to observe that for the gliding arc, not many people, or almost no one, cools electrodes. There are some reasons, but one of them is that there was one literature trying this and then saw some corrosion of the electrodes. Therefore, people probably didn't do that. But for the plasma processing guy, it's quite natural to do that. So that's why I did it. And these are just examples of what I have designed and built. There are two tubular electrodes, and water or air can be fed. In some cases, I fed the air in the tube and afterwards feeding the air to the plasma source. Then in this case, water is unnecessary, but obviously, water is more efficient. Therefore, in the normal experiment, I always used water. Then plasma was quite nicely extended, so I tried surface modification of this. This is glass fiber reinforced polyester, which is used for the blade. It's the same material which blade manufacturers are using. Then, but before that, I made a small characterization of the plasma by detecting optical emission from the plasma. It's an optical emission spectroscopy is a very powerful technique without destroying plasma at all, but detecting some reactive species which can emit photons in the detectable range. There are many emissions, but among all, we noticed the emission of excited state OH. It's a bit longer than 307 and 8, 9, something. And then this emission is detected up to around 6 centimeters above the electrode. And I must tell you that OH is very oxidative agent, and it is said that it is stronger, even stronger than chlorine. It's very, very strong agent. And at the same time, I treated the specimen and measured the atomic elements on the surfaces, how it is oxidized. Then even up to around 6 centimeters, the surface is nicely oxidized. So these are kind of nice, happy agreements between the plasma diagnostics and the surface characterization. And then we jumped into the mechanical tests, having this nicely designed setup of the sandwich specimen called double cantilever beam specimen, treating both sides and having glue and cured, then make various different moments of opening and shear stress. But then I probably have to focus on two different things. Black is with the normal mechanical roughing called peel ply, and blue is by plasma. And I'm happy to see that in all cases, plasma treatment consistently show higher fracture resistance. So, okay, then I have to talk just a little different from adhesion stuff, because I've seen something quite interesting and unexpected. It is related to, we call it plasma dosimetry. It's an analogy of the dosage amount measurement of X-ray or gamma ray. And the specimen is alanine. It's a kind of standard material for this area. And the idea is why not to use it for measuring the dosage of the plasma. However, we realized that it is coated with fluoropolymer. It's probably PVDF. It's a 20 micrometer. It's very thick. Therefore, I doubted if there would be any effects. But anyway, we tried it. with it's not gliding arc on this page, it's with DVD. Then we had a clear fingerprint or indication of creating radicals in the alanine. It was quite surprising, and I was a bit in doubt about it until the end of my research. But then, obviously, I compared the effects with DVD and gliding arc, and then saw a very huge difference between them. For this specific condition, DVD can affect the property of alanine beneath the very thick fluoropolymer, but not with the gliding arc. But on the other hand, if it is surface, it's quite different. You can see the red one. Gliding arc can affect the surface chemistry very much, reducing fluorine and increasing oxygen compared to DVD. So in these particular cases, gliding arc can be surface modification dominated, but DVD in this particular case can treat both of them. That's a kind of surprising result, which I wanted to share. Okay, and then plasma characterization diagnostics. First is just to measure the voltage current waveforms. That gives a lot of information. We typically use nearly sinusoidal excitation with the voltage. Black is blue is voltage, and red is current. We can see that current almost follows sinusoidal form, almost, with occasional, a little spiky stuff. So it's almost like DC resistance. Then I've been showing gliding arc photos with a kind of bulky discharge, but we tried with the short exposure high-speed camera measurement. Then we have seen something very different. It's in reality a kind of very thin, a few millimeters diameter, wire-like discharge. Since it is moving very fast, you can see the bulk one, but it's in reality. And then what was interesting is that plasma can stay there, even the polarization of the voltage changes. Therefore, we saw a kind of fringes of the strong emission and low emission in the photo in some cases because of the oscillation of the voltage. And that may be the secret why it can work very well. And then you can get the ignition at some point, then plasma starts to decay. But also something interesting is that in some cases we have some shortcutting events which can shorten the plasma. So it's a kind of very complicated behavior. But one more thing about the characterization is the finding of ground state OH detected by laser-induced fluorescence method. I showed another results of the excited state OH, but that is in the research column. But in this case, ground state OH is in the vicinity of the discharge, but not inside. And I think it has a much longer lifetime. And for the surface treatment of polymers, probably this OH ground state plays an important role for the activation. Okay, and I think I have to skip this part a bit. I did some stability analysis using a simple model, but probably more importantly, I made some experiments in order to have the longer extension of the plasma, because it's quite useful for treating complicated 3D structures. Then one of the problems of the plasma is that if there's a ignition, then plasma can extinguish. So it's nice if we can avoid ignition once we have a discharge. So I just physically separated two electrodes to see how it happens, and this is the result. And as distance is increased, the plasma tends to be elongated. But if it is too much, obviously we cannot have no discharge because of the requirement of higher voltage. So there must be the optimum gap exists. But maybe I would leave this for further discussion if necessary. And I demonstrated long life duration of the plasma, long extension, and OH radical generation for surface modification, and improvement of the mechanical properties in this. But then I also want to shortly explain second big topic about ultrasound enhanced plasma. The idea is that if you want to treat material using a plasma, you want to generate a plasma above the specimen, but then there is typically a sticky gas boundary layer sticking on the surface, which can disturb efficient treatment. If we can remove it or reduce the thickness, that would be probably better. Then it can be probably achieved by introducing acoustic energy from the top. That's the idea. And then this kind of very simple setup was designed with DBD concept, but we have mesh electrode so that acoustic energy can pass to the surface directly. So this is the first generation device. And then this is the result of the treating, again, blade material, polyester with glass fiber. And then I measured the oxygen content. Consistently, you can see the blue one with the black one. Consistently, after the plasma treatment, oxygen content increases. But with ultrasonic irradiation, oxidation is enhanced. But this is as expected. But there are a few unexpected things that makes me quite exciting. I noticed that the arc can be suppressed if ultrasound is irradiated. In the case of air plasma, we often saw arcing, even though it is DBD, because I try to have relatively high power. And also, it is known that surface can be uniformly treated. Some heavily oxidized spots can appear with air DBD. But with ultrasonic irradiation, surface became very uniformly treated. Okay, so in addition, another thing is that I played with different frequencies of generating plasmas, and in the case of low frequency stuff, I didn't have any sophisticated circuit, so I could apply only a very, very tiny power. Then I saw that with ultrasonic irradiation, wetting significantly improved only with ultrasonic irradiation. That's something quite interesting. So, and then I also combined these techniques to verify that combination is not only with DBD, but gliding arc can be also combined. But I think I have to skip it. Then future perspectives. Just briefly, there are, of course, obviously a lot of things as challenges in this area. In particular, chemistry-related things are not seriously studied, unfortunately. Gas reactions, surface reactions, and also influence of the ultrasound on the surfaces should be tested. Okay, I think I have to finish scientific part, but these works were not completed without a lot of significant support and helps from many of my colleagues and co-authors and inventors, and also some administration. So I'd like to thank to all of them and all of you. But in particular, if you allow me to spend maybe 1 minute, I'd like to thank the two people among them. One is sitting here, Bent Sorensen. Without his approval and consistent support, I couldn't finish this work. So it's, I want to have a special thanks to Bent. And another thing is Dr. Frank Leopold. Immediately after I came to Denmark, I worked with Frank, and he appeared most frequently to my publications. And he also gave a lot of signatures for this thesis as well. So I didn't imagine that he couldn't show up for this presentation. He unfortunately passed away last year. But anyway, this is all of my presentation. Thank you very much for the attention. Yeah, thank you.
Thank you, please.
Yeah, okay. Yeah, okay.
Because you will still be on the podium.
Yeah, yes, yeah.
Thank you very much for this presentation. Now is the time if we have any exauditorial opponents who would like to speak up afterwards. No? Then I would like to move forward and ask the first opponent, Professor Alexander Friedman, to join Yukihiro Kusano on the podium. And you will then take over with your questions and discussion with the defendant.
So maybe I should.
Okay. Well, it's not so many people doing it microphone, but it's okay.
It is recorded.
Yeah, and also I'm talking to you. Can you hear me without microphone?
Yeah, sure. Yeah.
I know I'm joking.
Yeah.
I understand that our major function is to criticize you.
Yes. Yeah.
And then make a conclusion, right? Let me just start with a conclusion from my side that I like your work.
Thank you.
So thank you for that first. But I have a lot of serious questions, though.
Yes, please.
But I like your work. I like what you're doing. And I like what you're doing for 4 major reasons. 1, 2, 3, 4. 4 major reasons what I like about your work. Number 1, it is the first time I hear works which relates wind energy and plasma. And from my perspective, it's extremely important area. Each big conference on plasma chemistry includes presentation. Van de Sanden, it's a huge center in Netherlands for like future energy research and plasma research. So he's always relating plasma to nuclear energy. While in reality, a relation with wind is extremely important. Not only because plasma is used for making, like helping to harvest wind energy, but because you generate energy from wind, it's not like energy from power plant. You have this energy when you have wind. No wind, no energy. While consumption is like at night. It's way less energy. During the day, you consume more. So you have to work with all of this kind of stuff. So here, plasma can be significantly helpful because plasma is able to convert electric energy to valuable chemicals, to generate synthetic fuel. I don't know, now Denmark probably has no synthetic fuel, but actually fuel, and what's the price of gasoline here?
Yeah,
my feeling is high.
Yeah.
But if this technology will be successful, if wind energy will help to generate gasoline, it will be very important. And that's interesting because in the whole world, people, they keep in mind only nuclear. While wind has a lot of specifics. So that's, I think, very good area for you to continue. And that's what's reason number 1 why I like this dissertation. It's like a way to go forward. Reason number 2, it's a good choice of discharges. You choose gliding arc and you choose DBD. Well, you mentioned that this is 2 major, no, it is not 2 major non-equilibrium plasma sources, not at all. However, I like this choice, and mostly because it's my choice also.
Okay.
I also choose these two, and there's a good reason for that. When you work with atmospheric pressure, like you said, DBD is the safest discharge, because when you put the electric barrier, you cannot have high current. Remark. Bad stuff. You mentioned in your dissertation and your presentation even that you are able to create arc with the electric barrier. I doubt it strongly, because if you have the electric barrier, current is low, it cannot be arc, it's a filament. It's a little bit higher energy filament.
Yeah,
Still,
okay.
yeah, so it is not arc. Okay, but sure. But what I'm trying to say that choice of discharges is excellent. Very important stuff, that it is a way to go to other applications, both cases. Reason number 3, it's an application which you choose. Because when you have these discharges, you can apply it for different applications. You choose actually treatment of polymers. And why I like treatment of polymers, not only because it can be applied for like wind energy harvesting, it is way more, because today plasma treatment of polymers, it's a huge area, starting from electronics. But new stuff, plasma treatment of biological stuff, plasma treatment, plasma medicine, is significantly based on that. So you treat biopolymers, and actually, what is if you treat liver, human, during surgery, or you treat wounds, that's polymers. So what you are doing has a very significant possibility to go further to new areas, which are, so that's reason number 3 why I like what you are doing. And reason number 4, maybe the most important, is originality of your work. So far as I know, and I know almost everything in this area, I'm not kidding. There is no other person working in combination of ultrasonic and this kind of plasmas. And it makes you a room. It makes you a niche. And it's a very, very good for different kind of applications, including biomedical applications. Because plasma is used today more and more. Ultrasonic for medical application is used widely. So what you are doing, it's actually a door to go to this plasma medicine saying, okay, you know, I can combine the best of the two worlds, and I can go ahead, and nobody can say anything because you are just the first one to do it. I hope you have patents. Well, that's 1, 2, 3, 4. I think it's enough. So I just try to start with explaining why I like what he's doing. So thank you for that.
Yeah, thank you.
Now, second portion, it's a torturing. And I explain and I understand from Jens that I have 1.5 hours to do that.
Yes, yes, up to.
Up to.
Yes.
They're laughing, but it's not so easy, you know. No, well, but also they say that I can be shorter than that.
Yes.
And I divide my questions into 5 groups.
Yeah, okay.
The first group I call thermal versus non-thermal plasmas.
Yes.
So I think that the most, well, all questions are just important. But I think that people here, and you know that, but I wanted them also to understand that plasma can be thermal, lightning, and plasma can be cold, aurora, or plasma TV. Or where is my cell phone? My cell phone is in his office, but in cell phone we have also plasma. And it is plasma, when you see light, it means you see plasma. And it is cold. So there is a cold plasma and thermal plasma. When you treat polymers, you're absolutely right. You need cold plasma, because if you have thermal plasma, what's the temperature? 5,000, 6,000. It is not very healthy for patients. It's not very healthy for polymers. It's not very healthy for cell phones. You're right. What makes you believe that plasma you are working with is cold? You did not make measurements. You were able to make measurements. You made optical emission spectroscopy.
Yes.
But you analyzed only OH. Why you did not analyze second positive of nitrogen to see the temperature?
Yes. Yeah.
So why you did not do that, or maybe you did it and you don't want to show us your results?
Well, may I answer to this question?
Yeah.
Well, actually, we worked on measurement of the temperatures, and it is listed among the appendix. The reference in the B part. But because my contribution was not significant, I decided not to include it. I thought it's not fair to include this thesis. But by the measurement for the for example, for in my translational temperature was measured from the planar laser-induced Rayleigh scattering, having the density analysis by the scattering. Then the temperature of the gas was, in that particular case of the gliding arc, it was a bit more than 1,000 Kelvin. In my memory, 1,200 Kelvin. That's a gas temperature. Then vibrational temperature was slightly more than 4,000 Kelvin in my memory, but it changes in many cases. It was from the measurement of OH, P&R branches in my memory, and also vibrational temperature was around 6,000 Kelvin. But then electron temperature was I think it's by the software and the measurement of it's around 10,000 Kelvin.
But the minimum temperature which you're talking about is translational temperature, and it's about 1,200.
It's the gas temperature.
Yeah.
Yeah.
Question, which is like a rhetoric question.
Yes.
Is it cold plasma? If somebody will make you surgery and come with this temperature inside of your body, you will say, okay, it's a cold plasma? Or?
Okay. Yes. Well, but it depends on the handling of the material. Maybe I should maybe start. Well,
you are defending. I'm like, you know.
Yeah. Yes. We even treated polyethylene using gliding arc. Mm-hmm. But the important thing is that we cannot just expose the plasma with fixed specimen. We have to move it with the thermal release support at the backside. Therefore, if it is thin enough, then specimen is attached nicely, then you can treat polymers, but not for our body. Because,
not of the body. Okay. You think that polymer is easier? It's not. I mean, but what you are saying that if you move your finger very fast, across even the fire, you're okay. But you have to do like that, right?
Yeah. Yes.
So what you are saying, you can withstand high temperature, but you have to move fast.
Yes.
It's a very risky business, you know.
Yeah. Yes. Yeah.
So just first of all, in your dissertation, you claim that it is cold.
Yes.
While when we ask questions, you say, sorry, it is not cold.
Yes.
Well, still I like what you are doing, but my recommendation for future to be, I would say, a little bit more consistent in that.
Yes, okay.
Especially keeping in mind that you also use ultrasonic.
Yes.
And the major idea of ultrasonic is just to improve mass exchange, you're right, just to provide, to give possibility for OH and other reactive oxygen species to go to the surface.
Yes.
But don't forget that Lewis number is about 1, which means that, in this case, I am almost sure. So what does it mean? That like if you stimulate mass exchange, at the same time, you stimulate heat exchange.
Yes.
So for one hand, you will do the job, but from another hand, you will not have the hand if you just put your hand there.
Okay.
So be careful with that.
Yes. Yeah.
For your future work, which I very much like, but keep it in mind. The second portion of this question, well, that was like a little bit of...
Yeah, but that's important.
Okay. Yeah, that's a good point he's writing. Okay.
Yeah.
Okay.
Thank you. Yes.
Oh no, this process is not more than 1 hour and a half, so don't worry.
Okay.
Now, you just spent less time talking about DBGs.
Yes.
With DBD, the electric barrier discharge,
Yes.
situation is way better and way more in for you, because there is no so huge temperatures, you know, because temperature with current is limited by the electric barrier. Question, did you measure temperature there? Maybe you can just share data, because you have something written and something hidden. So
yeah, but we didn't measure all the time of the, but it was the rotation temperature, but it was typically around several hundred Kelvin, maybe 400, 500, 600 Kelvin.
Still,
because it's
but tell me, what kind of method did you use?
It's
to measure temperature.
Well, sorry. I think it is measuring the optical emission spectroscopy.
Yeah, but with the second positive of nitrogen or
no OH.
OH.
Yeah, no, sorry. It's sorry. I have to. Yeah, no. In some cases, at least OH, but I'm not sure if.
So let me just make it a little bit nicer for you.
Yes.
Bad news? No, good news. That OH, when you measure temperature with OH, the temperature which you measure, it's from electronically excited state of OH.
Yes.
And OH is so reactive, like you said,
yes,
that lifetime is very short. So actually you have this optical emission spectrum, you have this radiation, before this OH is thermalized. So what you measure is not temperature of gas, it's a temperature of OH.
Yes.
Which nobody cares. So this temperature is significantly higher than actual temperature. So the good news is that your actual temperature is lower.
Okay.
So if you measure it with nitrogen, you see something like 180 degrees or something like that. OH, it's a higher temperature. So good news is that actual temperature is lower.
Yeah, okay.
Bad news that you did not measure the temperature. But you'll do it in future. Good. So that was the first group of questions about thermal, non-thermal.
Yes.
So what I understand after your explanation, and it's probably correct, that gliding arc, in your case, was kind of a little bit thermal, while DBG was actually, I would say gliding arc is higher temperature than you predicted, but DBG is lower than you predicted. So DBG is good, gliding arc is challenging. Good.
Okay.
Second group of questions is related to type of discharge which you have. You mentioned a couple of times in the text, not in your presentation, that it is a Townsend discharge.
Okay. Yeah.
So first, my question is why you think that it's Townsend discharge, but let me just explain to everybody, because if not, I'm not sure that people understand what we are talking about. When you have this arc moving, one of the big problems and the major idea of gliding arc when they just first invented and made it is to make arc very fast moving across the electrode to avoid erosion, to make it like a longer lifetime, safer, better, etc., etc. Now, arc is based on the so-called thermionic emission. So you have to be able to take, when you have like these two electrodes, you have to be able to take these electrons out of the metal. So there are two possibilities to do that, cold and hot. Cold, it is the so-called Townsend mechanism, or secondary electron emission mechanism, which is very, very good. So what is going on in this case? You're not supposed to increase temperature of the metal to a couple of thousand degrees. It's just like ions, once in a while they hit the surface and just electron is emitted, So it is safe, nice, good, excellent. It's a Townsend discharge. Bad situation, when you have like a high, like a very bright point, and you have like a couple of thousand degrees, and they emit electrons, a thermionic emission. And it's a big deal. It's not like a question of terminology. It's a question, do you have or you don't have corrosion, erosion, emission, whatever, of material? You, a couple of times, put in your text on your dissertation that you have Townsend mechanism, which means for engineers, you're doing very good. Do you have any proof that it's a Townsend mechanism, or just it's your suggestion? I hope you're right.
Yes, that's kind of probably a problem of my part. The description was basically based on some references, but not for gliding arcs, just for the, so maybe it's, yeah, in some sense it's not very appropriate. If then secondary process of ion bombardment for secondary electron emission is has to be included. Then I would say I'm not sure about that. And also in the case of high pressure plasmas, some people argue that it's more for streamer formation, for example, rather than having the Townsend mechanism. Yeah, so that's I don't know if I but I actually want to show one video about especially about obviously when there's no electrode and there's a short-cutting event, there's no solid material on either of the fruits, so there must be no secondary electron emission even if ions can bombard the plasma column. So
let me just clarify a little bit. So first of all, when we are talking about breakdown, creating plasma, there is two things here. Plasma in volume, that's what you are talking about. Streamers, not streamers, very important for chemistry, processing, blah, 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 etc. Another group of questions, which is the topic which we are talking about now, is what is going on the surface of electrode. Because to have breakdown, you need two things. One, you have to ionize gas. But also, when gas is ionized, there is a current, AC current, whatever, but it's a current. So electrons supposed to be able to go from the metal to the gas. And there is two ways to do that, cold and hot. And again, cold is good, hot is bad. Hot is bad for two reasons. Reason number one, you treat this your polymers, but we have high temperature. Material from your electrodes will go to the polymers. Or to the human body if you treat human. Not good. The second reason, why it is bad, it is actually you destroy electrodes. Like next day, or like even earlier, you say, oh my gosh, it's not good electrode anymore, I have to put a new one. Cold emission is good. And people working with gliding arcs, usually they're very, very, very careful to work in regimes of the so-called cold emission or Townsend emission. So my question to you was, do you analyze what kind of emission you have? At least can you provide data, if not physics, so at least how your electrode looks next day and what's the lifetime of your electrode? Or, and maybe you know how much metal goes to your polymers. So do you have any proof that you work in cold regime? I hope you work in cold regime.
Well, yeah, I also hope so. But at least I didn't detect any metals on the treated surfaces. But every time erosion may be quite tiny. But anyway, and also about
erosion? It was a little bit of erosion.
Yeah, but they are not detected on the treated polymer surfaces.
So I remember it was a guy, Lavoisier, I think. There is a law of material conservation. If metal left electrode, this metal is supposed to come somewhere. Where is the metal?
Yeah, but
the
also
easiest way for metal is to go to your polymer.
Yes, yeah. But also, I also want to mention one example of the gliding arc sources, which have been used, I think, already 5 years. So I suppose it was run many hours already, because I sometimes had to run the discharge for 30 minutes, 40 minutes without stopping. So maybe cooling the electrode helps a lot. But also the power regime.
It's like when you are cooking something on a hot pan and you do. It is not very much helping, because it's 1,000 degrees, couple of 1,000 degrees versus water temperature. What I understand, that you believe that other people, they found good regimes, and you try to follow these regimes, and you did not analyze at this point that you work in the best regime, but you hope that in future you can improve and find really the best regime. But now we just use data from other people without special analysis. Okay, thank you. It's just answer for future. Measure it.
That's okay.
Okay. It's not more than 1 hour and a half, so don't worry. Question number 3. Different types of DBD and different types of gliding arc, and why you choose the old one. Let me explain. Let me just explain to everybody what I'm asking, and to you also. For example, you start working with the electric barrier discharge, DBD.
Yes.
And you say that there are the filaments.
Yes.
And you try to find the regime without filaments. All your problems, because you are using the electric barrier discharge, 100 years old. Seriously. The electric barrier discharges was invented in 1857 by Siemens. And that's what makes Siemens. Because this discharge was immediately applied to generate ozone. They did not know that it's ozone, by the way, initially. And then surface treatment in 1870s and 1880s. It's all discharge. Now, today, and that's what you are doing. You just move one electrode, another electrode, the electric barrier. And sinusoidal voltage. People, if you look through literature today, they are not doing that. To avoid all these filaments, what they do, they use short pulsing. And when they use short pulsing, like most of people, they use, like if treatment of materials, they use microsecond pulsing. In this case, filaments are way weaker. But if you want to, because we go with the electric barrier discharges inside of human body, so it should be, so in this case, it's a nanosecond pulsing. To have everything uniform. That's the situation with DVD. Okay, let's start with that. Why you used old-fashioned DVD instead of using DVD which other people they use, like a modern DVD?
Yeah. Okay. Obviously, one big reason is that it is much cheaper to use normal sinusoidal waveform.
Okay.
That's
so you said that it's cheaper. You see that? Let me disagree with you.
Okay.
Price of electronics changing extremely fast, especially last 5-10 years. 10 years ago, microsecond pulsars, they were a couple of times, not more, more expensive than sinusoidal. Today, they have the same price. Nanosecond pulsars, you're right. Today, they are maybe 10 times more expensive. But at least go to microsecond, it's my strong recommendation, it will help you.
Okay.
So just to use, it's like, it's like people were sitting with like a cell phone. I don't know, my cell phone is in your office. people there sitting with cell phones, and you are sitting with, like, you know, calculator this big. It's kind of, for research, not good. I think that your vice president for research will help you. We are talking about hundreds of dollars. It's not more than that, so don't worry. Suggestion is to go to modern DBT.
Yeah, okay.
Good.
Yeah.
Now, the second part of this question, and you see that, her name is Catherine. When I mentioned to them, she wants to give you a little money to buy this better device.
Yeah, okay. Very good. Really.
No, well, you're doing like that, so it means, but we are talking about hundreds of degrees, hundreds of dollars, it's not huge amount. Okay, the second part of this question.
Yes.
The second part of this question. Why gliding arc, which you show.
Yes.
It's a gliding arc which we used to do in 1980s with Albin Chernyakhovsky. Hello, it's old. Have you seen modern gliding arcs? Probably yes.
Yeah.
Like the second generation, it was like all this tornado, etc.
Yeah, yes.
Now it is 2 cylinders. That's it. That's what they use now in automotive industry. You know, a couple of weeks ago, it was a big presentation from Korean, whatever. It stay on their cars, gliding arcs. But it is obviously not like that. It is the same physics, but it's 2 metal cylinders, and arcs, they are rotating one leg on one cylinder, another, and they are kind of close to each other to avoid any kind of problem, so just it's protection. So that's what they use as a gliding arc. And you use, again, like you said, gliding arc was invented in 19th century. It's right. So why you use discharge from 19th century instead of using like a modern discharges? Gliding arcs. With the same physics.
Okay, yeah.
And here we are talking about $10.
Actually, I'm not sure if I would have the newest update of the atmospheric pressure plasma sources. And for the surface treatment applications, I just knew some German companies providing a plasma treat device. So basically, that's a kind of.
But plasma treat, by the way, you're right.
Yeah.
It's a little bit different, but still, even plasma treat, they have cylinders.
Yeah. Yes.
Not that.
Yes. We had.
It's commercial.
Yes, it is. Yeah. But.
I'm sorry. You know the good news?
Yeah.
That when you buy something, in this case for gliding arc, 95% of price is a power supply.
Yeah.
It's only a little bit for these wires, etc. So you do have power supply. The only thing you have to do is, instead of your 2 wires, to put a piece which you can either buy, or I'm sure that you have abilities in the university to make it. It's not very difficult.
Yeah.
But you can buy it cheap.
Yeah.
So.
Yes. Well, my experience was that unfortunately I didn't have exactly what they are selling, but we designed a kind of similar ones in the lab and tested how it works. But for example, about the extension of the plasma was much shorter in my case, at least, and also the feature of the plasma showing up outside, because we are trying to treat relatively huge 3-dimensional structure in the open air. So I need something extending outside of the air. But then seeing the performance of the plasma, I felt just the feeling, but it had too high gas flow to extend the plasma outside. And my impression, but the effect or non-equilibrium condition is not good enough. That was my.
Okay.
Yeah.
What is my recommendation still is, when you continue working with what you're doing, is try to find with new configurations.
Yes. Yeah.
similar regimes which you already found with this configuration.
Okay, yeah.
And it is actually the same both for DVDs and for that, because you did a very good job, just physics-wise, chemistry-wise, analyzing and finding the best regimes. But maybe now just the next step would be to go to modern configurations, because they have, in both cases, they have one very significant advantage. They are safe here.
Yes, yeah, that's true.
And when you go to industry, to actual application, when you go with these two wires, it will not work. When you show at least plasma treat is in Germany, by the way. You know where is plasma treat? In Stuttgart, if I'm not mistaken. You see, she is laughing. Because she's also related to this city. So that's a commercial company which are selling these devices in a safe way, nice way to be used. Okay, good. Question number 4 and 5, they're easier. Question number 4. Keeping in mind, especially for gliding arcs, that gliding arc has a high temperature zone, low temperature zone, etc., and it's all in contact with surface. A question of uniformity of treatment. Do you have any data how uniformly you treat the surface? Because I would be afraid that in some points, it's like like cooking.
Yes.
When you're cooking, you try to have a regime and like all parts of the whatever it is, piece of meat is treated in the same way. And here you have in some points a couple of 1,000 degrees, and some points you have like 100 degrees. So, and this stuff is running.
Yes. Yeah.
So, what can you say about uniformity of your treatment?
Okay. Yeah, that's quite important. In my assessment, I always move the specimens and exposing the surface a plurality of times, so that at least we can avoid somewhere which is just accidentally wasn't exposed. But that was one thing. And the other thing is that although I didn't do a lot yet, but because utilizing the opportunity for long extension, and I also tilted the gliding arc so that the gas flow becomes much smoother than just vertically approaching to the surface. Then, how I can say, but maybe it's not more for treatment effects. But yeah, basically.
Okay.
Yeah.
I hear you, but you see that you have to keep in mind that this arc is moving kind of fast. And actually, you did not give number, but I would expect something like 30 meters per second, 10 meters per second, like a velocity of arc electrically moving. Gas moves slower, but not much slower. And when you move your substrate, it is way slower. So I would say that, if you want to catch the effect, it's better to control gas flow, not... It's like, you have a problem with like a grilling, and you will just move the piece of meat around just very fast. I mean, it's better to find a uniform regime.
Okay.
It's just my recommendation. But you did not mention one stuff. In your experimental system, when you just already measured like a carbon to oxygen contact, where did you measure it? Because in different part of the specimen, it can be different. So where did you measure it? And do you have any data on uniformity of treatment?
I usually measure at least 3 points. Then, average them. That's the way I...
I got it. But these 3 points, and you take the average. Like a difference between minimum and maximum is big or small? Like you gave number of like 30% or something. So what is a...
maybe, maybe it's not the XPS, but I just made some contact angle measurement already.
You made 3 measurements. I just asked how different are they?
Yeah. Well, it depends on the treatment. I mean, if exposure time is only once or twice, then it can diverse a lot. But if it is treated...
okay, got it. So just your approach is just to make it many times at some point.
Yeah, yes.
Okay. In future, again, recommendation is better to find more uniform regimes and to control this stuff with gas dynamics, with modeling maybe. But good, I understand. And the last question, I would say, the easiest probably is a mechanism of gliding arc ultrasonic interaction. I understand that you are talking about like mixing, which is good. But do you have any data just explaining and showing that this is a mechanism? Because I can give you a couple of other explanations. And you also, I'm sure you have not only one hypothesis. So do you have any proof, experimental proof, of synergistic effect between ultrasonic and gliding arc, and with DBT as well?
Yeah, okay. In the case of the, but this is, honestly speaking, a weak point. We are thinking that we have to do it. That's why we formulated a grant application last year, waiting the response. But what we have observed is, for example, with the gliding arc and ultrasound, although the aim at that time was not for that. Therefore, the photo I have taken was not very optimal. Okay. But we have seen some differences when ultrasound is irradiated or if there's nothing. And then, although I didn't mention about the influence on the discharge column itself, but there can be some effects as well also.
Okay. Thank you very much. How would they say in court? I have no more questions. What I have to do? Oh, but I'm satisfied with your answers.
Yeah, thank you very much.
Thank you.
Thank you very much, Professor Friedman. And thank you. Yeah. Then I would like to ask the second opponent, Professor Dennis Dowling, to come to the podium and ask your questions to Yukihiro Kusano.
Like Alex said, I'd like to firstly congratulate you, Yukihiro. Some of the work you're doing is very novel, and it's great to see a new area. And I think the ultrasonic addition into the gliding arc, as well as the DPD plasma, is something that's very unique, and it's very interesting to see the performance and the enhanced performance and the difference in performance that's achieved. Alex has already covered some of the questions I'm going to cover, so my section won't be as long in terms of the questions, but I suppose I'm coming from an engineering background, and I'm going to kind of look at this as more as an engineering problem, and maybe just look at it in terms of a process. So I know you're in a department which is wind energy department. You started your presentation by talking about the need for bonding, adhesion, and repair, and addressing those issues. Would you mind, can you still turn on your computer? I'd like to just put up one of the pictures and maybe just talk through the image. Okay. I'm particularly interested in, say, the gliding arc with the ultrasonic, the circular ultrasonic waveguide or cylinder just above it, please.
You mean the photo?
The photo, yes.
Yeah, okay.
Maybe I just want to talk through that photo per se.
Probably.
It'll be towards the end, I think.
This one?
Yeah, that's fine, yes.
Okay.
Okay, so taking that as an image, so I know this is a prototype, but I just wanted to talk through it in terms of its performance, in terms of an application, in terms of repair. So in terms of this, okay, so in this case, you have to do it at a side-on angle as opposed to straight down.
Yes.
Whereas in the DBD case, you're able to actually pass it through beside the electrodes, which would you say are the limitations with respect to this in terms of that approach, or what would you do in terms of designing this to perhaps to improve that design? So looking at that gliding arc arrangement there, because this is an experimental process,
yes.
But where would you take it from going forward? What would you do in terms of improving that? And the reason I asked you that question is I want you to talk about the limitations.
Yes.
In terms of this design and this equipment.
Yeah. Okay. Are you asking about the?
I'm very much looking at it as a system for doing what you said at the very beginning. You want to repair turbines, wind turbines. I know it's a prototype, and I know there are. What you have effectively done is to look at what are the limitations, how effective is it in terms of treatment, what's the effect of adding the ultrasonic energy to it. But I'm also interested in what your general comments, as a person who's developed a new design and a new system, what your thinking is on it, and how you would benchmark that system.
Okay. Well, it is actually probably related to the eventual application, probably. In the case of, many of my experiments, addition of ultrasound is not significant, I would say. In some cases, it could be substituted by just increasing the power or changing the frequency or any other things. Then maybe acoustic assistance is not very important, because once adding one more parameter, that can make a lot of complexity.
Mm-hmm.
Yeah. So yeah.
Okay, now I'll let you go on. I'm going to go back on each of these as you go through them. But
yes. Yes.
I'm not going to interrupt you. Let's just
So
you saying what you think are the advantages and limitations.
So as I said, it depends on the applications what we would do. Then what I'm thinking about the small changes is that the treatment, chemical modification by plasma is taking place in a moment, maybe within 1 or 2 seconds, usually, with, for example, DBD.
Yes.
If it is treatment of polymers, chemical reaction without etching is in a moment. Then it is saturated already. But then if we see the small difference of with and without gliding arc as the actual difference, which cannot be achieved without ultrasound, then there can be a room for designing a device combining ultrasound.
Okay.
Therefore, sorry, maybe I didn't still answer to your question.
No, you are.
Okay,
so really what I'm getting at is to look at this as a system and kind of say, as someone who's developed or proposed a new design,
yes,
you've assessed it on a number of levels. So if I'm looking at this as, say, an engineering perspective, I'd say, right, if I'm going to use it on blades, it needs to be fast, and it is fast. Mm-hmm. It needs to be, the input costs, you talked about the generator cost being 95% of the cost. The input costs have to be reasonable. So the question is the input costs, is the cost of repair, the bond strength, how does that work? And I know that's not really part of it, but you do mention in chapter 7 of your thesis. Ease of use is important, and it seems to be relatively easy to use, I would say, in terms of what you described. The reproducibility, and we're going to go talk a little bit about reproducibility in my questioning. The system reliability itself is also important. And then, of course, the key issue, does it work? Do you get the bond improvement? So in terms of the design here, did you say that you didn't feel that the ultrasonic has a big effect or not?
In this particular case of combination,
yes,
the improvement is, I would say, consistent. So I can say there's improvement or change by ultrasonic irradiation, but it's not significant in this particular combination.
But in general terms?
In general terms, it depends on the conditions.
Yes.
In particular, maybe it's not very easy with gliding arc, but with the lower power plasma, this can be significant.
Okay.
In some cases, for example, in the outdoor use of plasmas, you may prefer much lower power for operation. But then if you would be happy to use ultrasound, then it can be overcome by assistance of acoustic energy input. So that can be a kind of application we can think about.
You mentioned in your thesis that one of the impacts of the ultrasonic was that you get less arcing, you get more homogeneous discharge. Mm-hmm. Were you able to quantify that? Or were you able to determine that?
No, unfortunately, I didn't do that yet.
Okay.
So, and also, it's a pity that I cannot clearly explain what is happening. Why? Because I saw, for example, with air DVD, I saw a lot of filaments with or without ultrasound, but the treated surface is very different in terms of uniformity. So,
okay, but what do you think is the effect? I want to talk about the uniformity of the tree surface later on, but what do you think is the effect of the ultrasound in terms of suppressing arc formation? What do you think is the reason that it's working?
Yeah, I again have no clear answer, but the one literature says that acoustic energy can affect the plasma column if there is. It can expand the plasma column by acoustic energy for some effects. For example, reducing the temperature just a bit.
Okay.
But this is not related to the surface.
You had an image earlier on where you looked at mixing. There seemed to be some sort of a mixing effect of this interfacial layer. Do you think there's some sort of it's enhancing the mixing?
Yeah. Yes.
Okay.
I think there must be the mixing effect.
Okay.
As well. Yeah.
Okay, so in terms of design, Alex asked you the question about reproducibility, and you mentioned 3 measurements. Mm-hmm. Now, do you think that 3 measurements would be appropriate or would be sufficient in terms of a system like that? So you have a layer or a polymer sheet passing underneath this thing. Incidentally, how did you manage to... I presume that the polymer moved and the discharge was constant or fixed. Was that how it worked?
Yeah.
So how did you move the polymer? Or the composite?
There's the stage, one-dimensional stage moving forward and back.
Okay, and what sort of speed?
It's around less than 180 millimeters per second.
Okay, it's relatively fast.
Relatively fast, yes.
Okay, so in terms of the discharge, if you only take 3 measurements, do you take them at the same 3 points, or how do you measure those? So what I'm getting at is, if this here is the polymer, and say my book here is the discharge, you have a circular ultrasonic system coming down, and you have a fan-like discharge coming from your gliding arc. It's likely that you're going to have big variations because it's not a homogeneous discharge. So I suppose the question then is, what level of reproducibility? What was it like across the surface, and what? You mentioned you only did 3 measurements.
Yes.
You've partially answered the question already, but I'm just wondering where you feel this could be improved.
Yes, for the XPS measurement, because of the limitation of the access so long. So but I just randomly took the locations. But maybe I may want to mention probably the final attachment. I have the measurement. It's not average, but each measurement. This gives the idea of the scattering of the data. It's not, perfect, I would say. It's in the final part of the pages. It's I just have to recall if it is, I don't think there's a gliding arc at that time. Or did I? Sorry, I just forgot it. Yeah. But it's just a tilting and then also gliding arc. It is, there's no page, but in the last attachment of the,
is this in the
page 286 or something.
Was this in this one as well?
Yeah, yes, it's in the last. Maybe next.
It's the last paper, is it?
Yeah, it is. Yes, it is. Yes, it is.
Okay.
Yeah. Then.
Okay, so you have the images there showing it.
Yes.
Okay. So in terms of this, you are addressing it.
Yeah, I actually did it, but it's in this case, obviously, because I have to measure each point by droplet measurement. Therefore, there's no average.
Okay.
Yeah, so that gives me...
No, that's fine. So what you described, you began the thesis by saying, look, gliding arc, people have used water cooling. Mm-hmm. They seem to have stopped. You made a comment to say, look, not too many use water cooling. I'm assuming because with erosion at the outside, you're going to get a hole at some point and the water will come through and spread onto everything. Was that the reason why they stopped using?
I actually don't know, because the paper didn't clearly explain.
Yeah, you had highlighted the problem that there is. But then you decided to go and do the very thing that you said had been a problem.
Yeah. One possibility would be that, but I don't know about the condition, but the cooling temperature may be too low with some condensation.
Okay.
Before using, that may have a problem if it is metal, but I actually don't know. The paper just mentioned surface corrosion.
Sure.
When it is cooled with water, but nothing in detail at all. Okay,
now Alex asked you the question about metal being spread from this, because the metal has to go somewhere, but probably the concentrations are so low because the rate of corrosion or erosion is low. But is there a higher rate of corrosion in a situation where the electrodes are water cooled than the case where they're not? Like, I'd imagine where they're not water cooled, they're going to be a lot hotter. Is corrosion? I'd imagine the corrosion is going to be higher when they're hotter, no? When they're hotter, when the electrodes...
Yes, it is, yes.
Okay,
yes.
so you'd expect that it would be reduced in your design because of that?
Yes.
Or did you look at the electrodes after the deposition to see what level of damage occurred on them?
Well, for example, maybe this one is actually for some patent reason. For this initial experiment, I couldn't use the water-cooled one. Okay. Then I actually have this one in my bag now. Okay. But it is heavily corroded.
Okay. So that's the non-water-cooled one, is it?
Yeah, it is not cooled at all. Heavily corroded all over the places of the electrodes. That can give the instability, of course, because of the insulating layer at the beginning. It should be broken for the direct current passing. And of course, it becomes red, as you can see.
Okay, red hot.
Hotter, and then so it is serious.
So the other example doesn't. So therefore, it enhances its reproducibility. By water cooling. And are you, in terms of the designs, did you look at different designs in terms of the electrodes, in terms of getting water in there? Because you know, trying to get water close to the tip of that electrode where you need the most cooling could be quite a difficult challenge. Or did you look at the design of the electrode in terms of water cooling? So in other words, if you have a tip here, you want the water as close as possible to that tip. Take into account if you get erosion, it will leak. So did you play around with the design of your water-cooled electrodes?
For the stability, I didn't do that. But basically, it is I relied on the skill of the technician.
Yes.
And then a very skilled technician did very careful work for bending, modifying the tube. Okay. If it is just roughly done it, then it doesn't durate a lot. Okay. I had some comparison, but with the same design of the water cooling, it was quite different. Okay. Yeah.
So moving on from that then to the actual treated polymer, you had an image up there which showed the two spots on either side of a treated composite, and you compared a DBD versus the gliding arc. You know the image that you had where you got the two little pinholes at both ends.
Well, it is. Do you mean?
The one with the two pinholes. It's a picture. That one there. Okay.
They are both DVD.
Yeah, I know. That's okay.
Yeah, okay, yeah.
So, sorry, I'm jumping around. Okay, but in the case of the DBD here, it struck me as I looked at that is that the one on the left has a much rougher shape on the outside.
Yes.
Okay, the one on the right doesn't. So you've got a surface which has an imperfection and an edge on it. And an edge in a DBD discharge will attract the plasma more so. The two damaged areas are at edges. So do you think that it's an edge effect as opposed to a treatment effect?
But there must be the edge effect as well. But
Sure.
also the discharge or current pulse changes by ultrasound. Maybe I would show one of the references of the, it's with 50 hertz plasma.
Yeah.
I measured in the case, it is a DBD with 50 hertz.
Yes.
And it is, I think, it's 50 hertz.
That was page 53 of your original. The original, I don't know if it's...
Yeah. And since it is ultrasound, should be no, it should be TBD with the maybe I could easily find it here. But the point is that when ultrasound is irradiated with 50 hertz setup,
Yeah.
the pulse width of the current becomes much shorter, smaller. Therefore, it is like doing pulsed excitation. It's different, but well, it has, I would say, nicer plasma
Okay, so
without heating too much. So it has a kind of relevance.
okay, so I'm going to come on to the 50 kilohertz one because that was on my agenda in terms of a question. But can I just ask you in terms of finishing this one off?
Yes, okay.
Do you think it's a real effect, or is it just the fact that in the case of the one on the left here was a rough surface and it just, you kind of had a concentration of a discharge just as an edge effect?
Well, there must be the edge effect, but it's not only this time, but I often, because I had to apply quite high power for DBD, for high-speed treatment.
Yes.
So even for this tiny area, I usually apply around 100 watt. Then another problem is that one of the electrodes is not covered with insulator, with mesh electrode. That also makes the possibility of having high concentration current.
Yeah, so you don't have a dielectric over the electrode?
Yeah, yes.
Okay, so it's not really a DBD in that case then? Oh, one is a target?
Yeah, one is covered.
Oh, it's not... Okay,
yeah,
okay,
bottom is covered and specimen is placed. Then upper plate, upper electrode is a mesh electrode.
Okay, that's fine.
Yeah.
So again, in terms of reproducibility, how many measurements would you make on a sample like this? For water contact angle?
Water contact angle, it's typically at least 10 points making average.
Okay.
Yeah, so that's
And in terms of the homogeneity across the sample like this?
Yeah. The electrode is only 50 millimeters.
Right.
So if it is within 30 or 35 millimeters diameter, then it is, in my memory, it's within around 80% of scatter if it is contact angle. 80%. No, sorry, 80, so I mean 20%.
The 20% variation?
Yeah, yes.
Okay.
Yeah. But after averaging.
Okay,
yeah,
so okay. And was this more, in terms of comparing the gliding arc with the DVD, which gave the more homogeneous treatment?
Well, for the very tiny oxidative stuff, gliding arc is free from having this kind of
the arcing, the pinholes
of heavily oxidized spots.
Okay.
So in this sense, gliding arc is always more uniform in this micro scale.
Okay.
Yeah.
You mentioned a few minutes ago about the 50 kilohertz treatment.
Yes.
And I was looking at your results, and you ranged, I think it was between 12 and 50 kilohertz was I think that's my recollection, the range that you evaluated. But you saw a dramatic effect at the 50 kilohertz, which wasn't there, say, at the 12 and 40. What do you think the reason for that is? This is with the ultrasound, sorry. When you combined the ultrasound, you can see it on the graph here. So at 100 watt at 40 kilohertz, they seem almost identical. In fact, you don't have any error bars there, which to know if there was a significant difference. But at the 50 kilohertz, or the 50 hertz, you found such a dramatic change. Could you just give us what you think is the reason for that?
It is related to, but it's just my guess, I have to say. But it is mostly about the chemical modification. So in this case, if it is DVD treatment of polymers, it can be completed in a moment if it is the density of the plasma is high enough. It's a case for 40 kilohertz and 12 kilohertz. But in the case, because the power is very high.
Okay.
But in the case of 50 hertz, plasma, you cannot see it by your eye because of very, very weak emission. So the density is much lower, requires much longer time for the treatment. That's why even with the gliding arc.
But the treatment time is the same, no?
Yeah, but I needed some one minute for having the clear effect.
Okay.
But in the case of gliding arc, maybe only a few seconds, we have something.
Okay. So did you do optical emission spectroscopy on these, looking at density?
No measurement for the quantitative analysis.
For that one, okay.
No.
And you highlighted the ground state OH was important. That was for the gliding arc, was it?
Yes, it is. Yeah.
Okay.
Yeah.
And so how did you quantify I know I'm jumping back now to gliding arc, sorry, but in terms of that, how did you know that was important? How did you? How did you establish that concentration? And was that through optical emission as well?
Well, we measured the emission, but we didn't quantify the concentration in the plasma.
But yeah, go on.
But since the gliding arc doesn't generate significant amount of ozone or atomic oxygen because of high temperature, the lifetime of these stuffs are quite low, quite short.
Sure.
Therefore, we don't have very strong smell of ozone. But so only understandable explanation was the effect of OH.
Of OH?
OH, hydroxyl.
And is there evidence from the literature that would be the reason? Or are you the first to propose that? Are you the first to propose that the ground state OH is the important one?
Well, I actually don't know. Maybe it's...
It's all over the literature.
Okay.
Yes, yeah.
It generates a lot of OH.
Yeah.
Okay. I just want to finish up by just talking about the fluoropolymer. This is the coated alanine. Do you have a slide there on it?
No, maybe I went too much. Yes. Is this the one?
It was the XPS results where you were looking at the change in concentration of the different species. It struck me when I saw this originally that generally when you're plasma treatment, you get an increase in oxygen concentration and a decrease in carbon in other species. Here you seem to be selectively losing fluorine, much more so. I was just wondering, it's obviously very labile. The fluorine on this particular molecule is easily lost.
Yeah.
I was just surprised that generally fluorine bonds are reasonably strong.
Of course, it depends on the conditions, especially with the use of the gas.
Yes.
But in general, fluorine-containing gas, it's not a polymer, but gases usually used, for example, CF4 and also cyclostructured fluorine molecules to cut the bonds between carbon and fluorine. So I think it is rather easy to cut fluorine bonds.
Okay.
Yeah, that is.
But the oxygen content, like the carbon content, actually increased. Do you think you're getting some form of carbon formed on the surface? Like it was a breakdown to, I'm more interested in, are you seeing some carburizing or some damage to the surface, producing a carbon layer, perhaps with some oxygen, as opposed to functionalization. That's really where I'm getting at.
Yeah. In some cases, I observed the lower binding energy of carbon, indicative of carbon, carbides or some double bonds or others, I guess. But
yes.
In this particular case, we didn't see any appearance of the energy, binding energy.
Yes.
Of, but I have to maybe confirm it. I think I only remember that I attached some XPS carbon oneness stuff. So if the treatment make carbonize graphitic materials,
yes,
there must be, if I understand correctly, there must be the additional binding energy appearing a bit lower than 285.
Okay.
But it didn't show up.
Okay, that's fine.
So therefore, in this particular condition, I don't think there's any graphitic structure creation. But we did observe these situations in some cases.
Okay.
Yeah. Yeah, if there is, but I don't think the color has changed too. Yeah. So that's a good point. Yeah, if it is graphite. Yeah.
Sure. But but could be at the nanoscale.
Yes.
It's okay. So taking this forward, you have a chapter 7 there, where you kind of say, look, these are things I'd like to look at. You talked about earlier on about the economics of it in terms of the costs of a system, and it's mainly the power supply associated with that. You also talked about functionalizing surface and combining it with the use of precursors. And Alex mentioned the plasma treat source as a commercial source, which would be not unlike it. There's a lot of similarities between them. Where do you want to go with this? What's the next stage in terms of bringing this forward? I suppose thinking in terms of a wind energy environment where bond strength is absolutely crucial. So achieving good bond strength is so important. So what's the next stage?
Yes, there are two very different aspects. One is obviously scientific interest of understanding of the plasmas, for example, with ultrasound or many other things. But for the department or for the practical application, one important thing is to have the optimized design of the power supply. That is power supply for the plasma. That is quite important. As Professor Friedman mentioned, the price of the power supply almost always dominates the cost, maybe around 90-95%. You can see that the electrodes are just cheap, almost nothing compared to...
but in the overall scheme of things, if somebody's repairing a wind turbine, it's speed and efficiency and never having to go back again is what you want.
Right.
So.
Yeah, but then the point is that we should have the efficient delivery of the energy to the processing. That is one thing.
Yes.
And it's often the case that only one device is not sufficient for limited time for the application. So we usually need a plurality of devices running together. Then if we need individual power supply, that's a problem. So one thing which should be considered is to share one power supply for driving several plasma sources at the same time.
Okay. But that may or may not be applicable in terms of a repair situation where it would be if you're doing a production process. My last question is in terms of process monitoring. So having talked to, say, a number of end users using these technologies, they say, well, we don't know if the surface was treated or not, because you can't actually put something onto the surface because that would contaminate it. So are there any... So in a sense, you have to combine the two together. You need a process monitoring to say, yeah, this surface was treated, but doesn't actually touch the surface. Have you any suggestions on how you would approach that problem in terms of, say, the gliding arc or the DVD sources? Okay.
It again depends on the application. If it is within the manufacturing process, it is usually quite nicely controlled with a limited variety. So it is rather easy to have the characterization. Easiest one is to have the occasional wetting test after treatment.
Sure, but you can't touch them.
Yes. In that case, we have to touch it.
Yeah.
Yeah. But
So in-process monitoring.
yes.
Is there something you'd suggest?
Yeah. But then it highly depends. Yeah, in some other applications, observation of the optical emission all the time.
Sure.
Then if you have contamination of water, then you will have something different that can be detected.
Okay.
But of course, it depends on the importance of the detection. Therefore, I have to see the real target of the application. Then depending on that,
Sure.
yeah.
Yeah, no, optical emission would be a good
one of the things.
one potential solution. Just as you mentioned there in terms of contamination of water, we have a plasma treat system, and if you have moisture in the air, you have real problems. So it's so important to have a dry source, but that's just by the by.
Yeah.
Look, thank you very much. Very interesting thesis, and clearly a very novel approach in terms of the introduction to this ultrasonic effect, and clearly the improvements you're making with the gliding arc are really innovative. So thank you.
Yeah, thank you very much.
Thank you very much, Professor Dow. I just have one more short comment question by Professor Friedman before we finalize.
Yeah, please.
It's actually not a question, but a remark, very positive, I'd say, remark, following your discussion with Dennis. Two remarks. First remark is effect of ultrasonic on all the behavior. And you show here dependence on frequency. And it was in your question. It is very, very important. And you did not put enough attention to that. It is very, very, very interesting and important. Because from the point of view of mixing, it is not so much question of frequency, while there is a very significant effect of interaction of ultrasonic with plasma because of vibrational relaxation. The famous work of Landau-Teller, 1934, which was a starting point for lasers later on. What is going on? You measure vibrational temperature, which is higher than rotational temperature. So there is a relaxation. It should be like a way for go from vibration to translational degrees of freedom. And when you have ultrasonic oscillation, they are actually at certain frequency. They are in a resonance with the time of VT, vibrational translational relaxation. And when this happens, you have significant increase, or vice versa decrease, of energy transfer from vibration to heating. We change the whole behavior of plasma and consequently treatments. So maybe that's what you observe. And it is very, very, very interesting from the point of view of physics, because it was in the center of people, they are very interested in that in 1980s, 1990s. It is interaction between ultrasonic and plasmas. So it is just in the lasers, the same effect observed in plasma treatment of different materials. So that's maybe, first of all, it's good, and pay some attention. Maybe you can publish a couple of interesting papers just on dependence on frequency. And at the same time, you will explain mechanism. It is just simply mixing, or it's a deep physics sitting there. The second remark is from the same, similar kind of stuff. It's a water cooling of electrodes. A lot of people now work with gliding arc discharges, and most of the people, they do not use water cooling because they are very much proud that they don't need it. That they use cold regimes. Now, you observe very interesting stuff, actually, effect of cooling cooling can, when you cool electrode, you cannot change the temperature of a hot spot when plasma touches, you know, when arc discharge touches the surface, temperature is enormous. With a little bit of water, you will not help it. What actually you do is, it's instability. It's a jumping from one regime to another. Because when arc moves along the electrode,
Yes.
I think that you saw that also in your photograph, it's jumping. And if it jumps, it's not good. Jumps mean it was a very, very, very hot, and plasma doesn't want to, you know, this arc does not want to leave this point because it's so nice here, so hot, so nice, but at some point it jumps. It's not a good regime because you actually destroy here, destroy there. When you cool it down, what you do, you try to avoid these instabilities. And as a result, what starts happening, you can influence transition between this famous Townsend regime and fermionic emission regime. So I would recommend you to continue research in this direction. These two areas, they can lead you not to big funding, but to very nice publications related to physics of the phenomena which you observe.
Okay, thank you.
Thank you very much. And this finalizes the formal defense of Yuki's thesis. And I should just give my... Congratulations to finalizing the defense.
Yeah, thank you very much.
And, I would again like to thank the opponents for joining us. Now your work is over, our work is over. We will go, and I hope you'll join us for the reception, while the assessment committee will go and finalize their work and join us after that.
So maybe we'll make a decision that it was too early with flour.
No, that was for the defense. That was just for the defense. And your recommendation is going to be passed on to the Academic Council of the University. So thank you all for being here today, and please join us for the reception.
Thank you very much.